All right, I realized I wasn't recording, so I'll go over what we started with. The first problem is a mechanism problem, which is halogenation of an alkene. So you need to set up your halogen molecule so that one of the halogen atoms is right near to the alkene double bond. We have an arrow showing the alkene double bond, the pi bond attacking that end halogen. We take a lone pair from that halogen atom and we attack the other carbon in the alkene, and we break that weak halogen-halogen bond. That gives us this intermediate over here. And the reason I'm drawing this chlorine with a dotted bond is because I noticed that in the product, the chlorine there has a wedge bond. So it's going to be an SN2 reaction. So remember that your halide ion attacks the more substituted carbon. That's also where the water molecule will attack if you're doing a halohydrin reaction. So the chloride ion comes from behind the chlorine that's in the three-membered ring. We break the three-membered ring, and we wind up with this dichloride. So that's it, 2 steps. The next one, when we analyze it, we see that we're treating this alkene with HBr, but the bromine doesn't wind up on either of the 2 formerly alkene carbons. That means we must have had a carbocation rearrangement. And so we start by setting up our HBr molecule in this case. And the alkene pi bond picks up H plus from HBr. This could just as easily have been HCl or HI, so don't memorize that it's always HBr because it might be HCl or HI. And that gives us a secondary carbocation. This is perfectly set up because there's a hydrogen next door on the tertiary carbon that we can move over in a 1,2 hydride shift to give us this tertiary carbocation. And so that's why the carbocation rearrangement happens, because we go from a secondary carbocation to a tertiary carbocation. And the tertiary carbocation is more stable. And then that's when our halide ion attacks the carbocation, and we get our bromide over here. The reason that there's no wedge or dot bonds over here is because this compound is not chiral. There's a plane of symmetry running down the middle of the 6-membered ring. So everything shown needs to be shown. Anything not shown is okay not to show. And I mean, I already have the answer key posted. But that's it for the first page. Please stop me if anyone has questions. All right, this one's a fairly simple one, actually, because, well, the mechanism's not so simple, but I certainly picked a simple starting material. Just propene. So as you'll recall, the mechanism starts, whoops, with our mercury 2 ion, and the alkene shifts out to form a bond to mercury, and there's an electron pair somewhere on the mercury. Mercury has lots of electrons, and that attacks the other alkene carbon. This really looks very much like the halogenation reaction. That forms our cyclic mercurinium ion. We then have water, attacking again at the more substituted carbon. So we take one of the lone pairs on the water oxygen, we attack the more substituted carbon. That's why we get the Markovnikov alcohol, because the water attacks the more substituted carbon. That pushes an electron pair onto the mercury 2 ion and reduces mercury 2 to mercury 1. So this is now Hg plus. So we get this intermediate. Next, we need to get rid of the plus charge on oxygen. And the way we'll do that is by deprotonating the oxygen with another water molecule. So water picks off the proton from that oxygen. Now it's just an OH group. And then in the last step of the mechanism, we have a hydride ion that comes from the sodium borohydride, NABH4. So you just draw the hydride ion in, and you show the hydride ion attacking the carbon that has the mercury on it. That breaks the carbon-mercury bond, pushes the electrons onto mercury, and reduces it from mercury +1 to mercury 0. You do get mercury metal out of this reaction. And that gives you the product. So that reaction is oxymercuration reduction. It gives you the Markovnikov alcohol from an alkene. The next reaction is an epoxidation reaction using metachloroperbenzoic acid, also called MCPBA. And what you need to know is you need to set up that per acid molecule such that the oxygen attached to the hydrogen is facing towards the alkene double bond. And it doesn't have to be MCPBA. The R group attached to the per acid could be methyl or trifluoromethyl also. Oh, I forgot my chlorine. There we go. So this molecule is the MCPBA, and you need to redraw it to get credit if this is on the exam. You need to redraw the molecule. And it needs to be redrawn such that the oxygen that's attached to the hydrogen is facing towards the alkene. And then we need 4 arrows. We need one going from the alkene to the oxygen that's attached to the hydrogen. We need another one from the oxygen-hydrogen bond going to the other alkene carbon. We also need to break that weak oxygen-oxygen bond. That's where all the driving force of the reaction is coming from. And then finally, we show a bond from the carbon-oxygen pi bond to the hydrogen. And that's it. It's all one step. That gives you the epoxide, which you do have to show, plus a molecule of metachlorobenzoic acid, which you don't have to show. Remember, you're always looking to establish how you get from the starting material shown to the product shown using the reagents shown. That's always the way this works. Always. There are no exceptions. But if anyone wants to see how you do get the regular metachlorobenzoic acid, I'll leave all the atoms in exactly the same place. This is the byproduct of the reaction. So there's a double bond over here. There you go. So that's the other molecule you get. This carbon here is this carbon over here. And you get the epoxide in one step. And that's it. The reaction's concerted. It happens in one step. Questions in either of those mechanisms? Actually, if I recall correctly, there's one more mechanism problem at the very end. We might as well take care of it also. So here we have treatment of phenylacetylene with HCl. We'll have at least 2 equivalents. Alkynes add hydrogen halides just like alkenes do, except the reaction happens twice. So the mechanism is the very same things we talked about in chapters 6, 7, and 8. So the reaction starts by attack of one of the alkyne pi bonds onto the HCl. Notice the directions the arrows go. We never use arrows to show movement of atoms. So you don't use an arrow to say this H goes here. That's wrong. Arrows always and only are used to show movement of electron pairs, never atoms, never charges. Always, always, always electron pairs. And we get this vinylic carbocation. We then have attack of the chloride ion. Onto that carbon. Actually, I think I'll draw this a little different. pH for phenyl group. pH can only be used for C6H5. It can only be used for a monosubstituted benzene. In other words, a benzene ring with exactly one thing on it. Exactly one. If there were more than one group on the benzene ring, I couldn't use pH. So we get this vinylic halide, and then the same thing happens again. We get this carbocation. This carbon on the end is now a CH3. You don't have to write out the CH3. I'm just showing it for clarity. It was a CH2, but now it's a CH3. So we've gained a total of 2 hydrogens from the HCl. And last but not least, fluoride attacks once more. And we get the product. So it's exactly the same mechanism as for an alkene, as for an alkyne. The only difference is with an alkyne, it happens twice. That's a chapter 9 reaction. Questions on that one? Next, we have some fill in the blanks. The first one is a reaction with ozone, followed by zinc and aqueous acid. We talked about this reaction in class. We said that you need to cleave the pi bond and put oxygens on both pi bonds so that you get C double bond O on both of them. But if you look, this is a symmetrical alkene. So both sides are the same. So you get two of the same molecule. It's 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. This alkene is symmetrical. And so you just get a 6-carbon chain with the carbonyl on carbon 3. I'll prove it. So you just draw the molecule once. That answer would receive full credit. The next one has us treating an alkene with aqueous acid. And in class, we said that this is an acid-catalyzed hydration reaction. This gives you the Markovnikov alcohol, but it goes through a carbocation if there is any chance of rearrangement. This mechanism doesn't go through any rearrangement. It just gives us the Markovnikov alcohol. So the OH goes on the more substituted carbon and the hydrogen on the less substituted carbon. And we get this alcohol. That's also a mechanism that you need to know. In the next reaction, we're treating this alkene with HCl. We've known this reaction since chapter 6. You get the Markovnikov addition of HCl across the double bond. The chlorine goes on the more substituted carbon, the hydrogen on the less substituted carbon. This one is a halogenation reaction. Maybe I should write these down for the sake of the video. No, you don't have to write the name of the reaction. I'm just doing this to help people for clarity's sake. And here we have halogenation of an alkene. Since we're treating it with bromine, that's going to add a bromine to both of the formerly alkene carbons. We don't need to use wedges or dots for the same reason that we haven't yet on this page, because there's no chiral carbons. This carbon has 2 ethyl groups on it, so it's not chiral. This carbon is also not chiral because there's a plane of symmetry running down the middle of the 6-membered ring. And this carbon is also not chiral because there's 2 ethyl groups on it. So no need to show any stereochemistry. There's no chiral carbons. The next one is hydroboration oxidation, which we covered in chapter 8. So far, these are all in chapter 8. Though we had some chapter 9 reactions on the previous page. And hydroboration oxidation gives you the non-Markovnikov alcohol. So you turn the carbon-carbon double bond into a single bond, and you add OH to the less substituted carbon. The opposite type of reaction of acid-catalyzed hydration or oxymercuration reduction. Those give you the Markovnikov alcohol. And last but not least, we have hydrogenation of an alkene, or reduction of an alkene. And hydrogen at H2 adds across that double bond. And the hydrogens add in a syn fashion, SYN. So we need to show that in the product. We need to show that the two methyl groups are cis to each other. You don't have to draw the hydrogens, but if you want to, they should be with dotted bonds. Whoops. Either way, the hydrogens are understood, so you don't have to show them if you don't want to. But you do have to show the stereochemistry. You have to show that you're aware that it's syn addition of the hydrogen. So these are not mechanism problems. These are just filling in the product.
I had a question.
Sure.
So you said we have to show the stereochemistry, so we would have to show the wedge bonds?
You could also draw it with dotted bonds. You could also draw it like this. It's the same compound.
But we couldn't just draw like the line?
No, you couldn't. That would lose points.
Okay.
Because it doesn't show that you're aware that the hydrogenation is syn. So that's something you need to know, that the hydrogens add from the same side of the molecule. You have to know the stereochemistry of the reaction. There were no stereochemical issues in each of these, but all of these reactions have stereochemistry. So you need to be, well, not ozonolysis, I suppose. So notice it says you must account for all applicable relative stereochemistry. But if the product is a racemic mixture, draw only one of the two enantiomers. If you incorrectly show stereochemistry where none exists, you may lose points. Let me just do an example of a hydroboration that does have a stereochemical issue. I'm just going to write BH3, THF. It's the same thing. It's giving me troubles. In this case, the boron and the hydrogen on the borane add from the same face of the molecule. You can also draw the enantiomer with the methyl on a dotted bond and the BH2 and the H on wedge bonds. But of course, it doesn't stay with BH2 because we treat this with aqueous alkaline hydrogen peroxide. So the final product is an alcohol, and the carbon-boron bond gets changed to a carbon-oxygen bond. And so you would need to draw either this or its enantiomer. And yes, if you just drew straight lines, it would lose points because it's not showing the correct stereochemistry. So that's part of knowing a reaction, is knowing the stereochemistry of the reaction. That's just an example. Other questions? Here's some structure drawing questions. PHF is a 5-membered cyclic ether. Looks like that. Sodium borohydride. Is a BH4 minus ion, which is drawn like this. With the sodium ion. Something like that would be fine. Trans 1-bromo-3-methyl cyclopentane. Actually, I'm not sure that belongs in chapters 8 and 9. That's more of a, well, it could be a chapter 10 question. It could be a chapter 3 question. You certainly still have to know it. One bromo 3-methyl. I'll just put in the numbering to help people see it. And then trichloromethyl in parentheses benzene. It did say it might be necessary for you to think outside the box a little. So there's benzene. What's a methyl group? Well, a methyl group is CH3. So what could a trichloromethyl group be? It would mean that you replace each of the H's with Cl's. And so trichloromethyl benzene, instead of a CH3 group, would have a CCl3 group. So I think there's enough information in that name to figure out the structure. That's pretty much it for that page. This one comes with some explanation. Addition of F2 across carbon-carbon double bonds is much less commonly seen than addition of Cl2 or Br2. And this journal article showed that the mechanism of F2 addition is more similar to addition of HCl, HBr, or HI than to addition of Br2 or Cl2. You do get a carbocation, and the second fluorine adds from the same face as the first fluorine. And all we're asked for here is the mechanism arrows. So it says the mechanism is like addition of HCl, HBr, or HI. So that means We have our alkene attacking the fluorine and breaking the bond between the two fluorines, just like adding HCl or HBr or HI. That gives this intermediate. And then you have attack of the fluoride ion onto the carbocation to give you the product. So that's all there is to it. Then it says draw a resonance structure that explains why the first fluorine adds where it does. So why is this carbocation intermediate so stable? And the reason is that the plus charge is next to the oxygen. And the oxygen can help stabilize that plus charge. So the other resonance form would look like this. So the plus charge is shared between the oxygen and the carbon. Then it says circle the phenol group. That would be the OH on the benzene ring. Then it says draw the conjugate base. Remember from chapter 2, the conjugate base has one fewer hydrogen. So it would look like this. And there's really no other proton that can get pulled off except that one. You're not going to pull off one of the aromatic hydrogens, for instance. That's the most acidic hydrogen. And the way you know it is because the hydrogen is attached to an electronegative atom. All of the other hydrogens are attached to carbon. So then it says to draw any one other resonance form of the structure to the left. Well, you always use curved arrows to help you find another resonance form. We can push the minus charge over to that carbon. Unfortunately, it's covering up the minus charge with a red circle, but that's a carbanion over there. The minus charge could also go on this carbon. It could also go on this carbon. So there are multiple correct answers to that question. So some of these are questions from earlier chapters. That's fair game. Organic chemistry is a cumulative field. You don't get to forget the material from past exams. In Gen Chem, you could kind of get away with that, but not in organic chemistry. You still have to remember everything from all the previous chapters. I should really have done this before. We already had questions of this format. The first one is oxymercuration of an alkyne. We went over that reaction in class. And we said that the product you get gives you an enol with the OH on the more substituted carbon, which is this one. And the enol then tautomerizes to the keto form, which is going to be a ketone. This is carbon 1. This is carbon 2. This is carbon 1. This is carbon 2. So you can see where the two carbons go. But oxymercuration of a terminal alkyne gives you a methyl ketone. We went over that reaction in class. The next reaction we're going to go over tomorrow So this is oxymercuration of an alkyne. And so let me actually save that one for last so that I can use the whole page to explain it. The next reaction is formation of a cyclopropane. And we're going to form a cyclopropane across that pi bond. And since the methyl group and the ethyl group are trans in the starting material, they will be trans in the product. And then so this is carbon 1. This is carbon 2. This is carbon 1. This is carbon 2. And then on the third carbon, wait a minute. I've got the wrong reaction. I'm so sorry. This doesn't form a cyclopropane. I was confusing this with I saw the halo form and I got confused. All right, cyclopropanation is a reaction in chapter 8 that we talked about. We talked about two types of cyclopropanation. However, this is not cyclopropanation. This reaction starts by forming the dibromide, Br over here and Br over here. That's the first step, Br2 in chloroform. That forms the dibromide. And then the excess base does two E2 eliminations and forms the alkyne. This is carbon 1, 2, 3, 4, 5. And this is carbon 1, 2, 3, 4, 5. I'm just putting in the numbers to give a visual aid. And you could call this one halogenation of an alkene followed by double dehydrohalogenation to form an alkyne. We talked about that reaction in chapter 9, at the beginning of chapter 9. So that's something we covered in class. The next one, we're treating this alkyne with lithium metal in liquid ammonia. That's a reaction we also talked about in class. That converts the alkyne to a transalkene. I'll even draw in the benzene rings. So these two alkyne carbons become a transalkene. If we wanted to make the cis-alkene, you'd need to use hydrogen and Lindlar catalyst. That gives you the cis-alkene. But lithium metal and liquid ammonia gives you the transalkene. And we covered that reaction in class, I believe, on Monday, yesterday. So in class yesterday, at the end, we said that NH2 minus, which is the same thing as NaNH2, NH2 minus is a strong enough base to deprotonate a terminal alkyne. And so you get this at first. This now is an excellent nucleophile and can react in an SN2 reaction. We'll talk about that tomorrow. And so we've got 1-bromopentane. That's what you see here in step 2. The nucleophile attacks the substrate. This is a chapter 11 reaction, essentially. And so the final product, the one you'd actually draw in your answer, you wouldn't show this alkynid anion in your answer. One, two, three, 4, 5. That's the answer. That's what you'd actually draw on the exam, if that question were on the exam, which it won't be, but something similar could be. I'll let you think if there are any questions while I take a quick bathroom break, and you can look at my cat. Yeah, move the chair. There he is. Poor sleepy kid. Poor Barnaby. Okay. And last but not least, we have half an hour to talk about synthesis problems, which we're also going to cover in class tomorrow. So the goal of a synthesis question, and you can tell it's a synthesis question because it says show the synthesis of two of the following three products. So what you need to show is a way of turning these two molecules into this molecule using at least two steps. And I have a step-by-step method for this in your Chapter 9 class notes, which I'll allude to here. So what you should always do first is count the carbons. And one thing I'm sure I'm going to say tomorrow is write it down. 1, 2, 3, 4, 5, 6, 7. 7 carbons. Write it down. They'll probably get you a few points. And then this also has 7 carbons. And then the product has 1, 2, 3, 4, 5, 6, 7, and then 6 more. Wait a minute, it can't be 13. Am I counting right? 3, 4, 5, 6, 7, 8, and 6 more makes 14. Good, okay. So this has 14 carbons. In other words, we've combined these two structures into this. Now, what you have to know in order to do synthesis questions is all your reactions backwards and forwards. You have to not, it's not just memorizing examples of what we did in class. It's understanding what the reagents do and why. So what I'm seeing when I look at this product is it looks like we added this whole thing right here. We just added that right onto the other chain. So a good way to solve a synthesis question is to work backwards. So how are we going to make this compound? What are we going to use besides obviously this? I say obviously because this is this same piece over here. So what's the other piece going to be? How are we going to attach this O to this C? How can you make a new oxygen-carbon bond? Well, in chapter 11, we learned that you can do that by an SN2 reaction. And so, if we can somehow get for example, this bromide, then if you treat this bromide with this benzoate ion, you will get the product. It will undergo an SN2 reaction, and I'll prove it to you. This will attack right over here, break the carbon-bromine bond, and give you the product. So now all we need to do is figure out how to make this bromide from this alkene. So let's compare these two structures. You have a tert-butyl group, then 3 CH2s, 1, 2, 3. Here you have a tert-butyl group, then 1 CH2, followed by an alkene. So somehow, we have to change this alkene to the non-Markovnikov bromide. That's what this is. This is what you would get if you could somehow add HBr in a non-Markovnikov fashion, which actually is possible, but we didn't go over that in class. And it's not in your book. So we don't know how to make a non-Markovnikov bromide. We do know how to make a non-Markovnikov alcohol. How do you make a non-Markovnikov alcohol from an alkene? By hydroboration oxidation. So that's a reaction that we know. Can you convert an alcohol into a bromide? Certainly you can. To get the bromide from the alcohol, again, we're working backwards. What would be a reagent that would turn the alcohol into the bromide? Well, we know a very good reagent from chapter 10. It's phosphorus tribromide. And diethyl ether solvent. So that's the reagent that we would use to convert the alcohol to the bromide. Once we have the bromide, we would treat it with the benzoate ion and get the product. So we're getting closer and closer to our starting material. In fact, now we can get from the starting material to this alcohol in one step. And that's just done by hydroboration oxidation. So you need to know all your reagents. BH3THF, followed by aqueous alkaline hydrogen peroxide. So the entire synthesis and what you would put for your answer is that we treat the given alkene with hydroboration conditions that gives us this alcohol. We treat the alcohol with phosphorus tribromide. That gives the bromide. And then we treat the bromide with the benzoate ion, which we're given. And that gives us the product. That's one way to write the answer. I'm afraid I've run out of room. You don't have to write all the intermediate products if you don't want to. You can just list the reagents: 1 borane THF, 2 H2O2 in aqueous base, 3 PBr3, 4 this thing, and then you get the product. So that's how you do a synthesis problem. You do it by working backwards from the product to the starting material. And you're asking at each step, how can I change? What can I use to get this product that looks a little more like my starting material? So this is a 4-step synthesis. This one's a little easier. This one, I think, only needs 2 steps. So we've turned this bromide into this alcohol. Now, is there any way that we can make an alcohol like this that we know of? We know how to make alcohols from alkenes. And that's convenient because we can certainly change this bromide into an alkene by doing an elimination reaction. We talked about that at the beginning of chapter 8, but I'm getting ahead of myself. So if we can somehow get this alkene, then we can again use hydroboration oxidation in order to put the OH on the less substituted carbon. That gives us the non-Markovnikov alcohol. And you need to know what are the reagents that will do that for you. Oh, there's something, and you probably asked a question half an hour ago. I'm so sorry. If you listed the reagents, would you also have to list the diethyl ether alongside the PBr3? Yes. Let me leave the chat open. So again, this requires borane and THF. Followed by aqueous alkaline hydrogen peroxide. That would convert the alkene to the non-Markovnikov alcohol. You see how we moved backwards from the product to a material that looks a little more like the starting material. And then the only question is, can we get from this bromide to this alkene? And the answer is yes, we can. All we'd have to do is an E2 elimination reaction. And that can be done with any strong base like sodium or potassium hydroxide in pretty much any solvent. You could use DMSO if you really wanted to make sure that it was E2 rather than E1. But I think with a strong base, it will go with an E2 reaction anyway. So this, actually, I guess you could say it's 3 steps. First, elimination of the bromide to make an alkene using an E2 reaction. So you'd write 1 KOH ETOH, 2 BH3 THF, 3 H2O2, H2O, and OH minus. Or you could write it out like this. This is totally fine also. Let me show you another way you can give the answer. Also perfectly acceptable. You don't have to draw the intermediate compounds. You can if you want to. And as you'll notice, you don't have to show mechanisms. Could you have done the elimination via E1 as well? Well, I don't think that's as good because remember, E1, what's the word I'm looking for? Competes with SN1. So if you just heated it in water, you'd get some with the OH over here. And I don't think that's as good. I think an E2 elimination is better because you want to be sure that you get the alkene in the highest yield possible. Would it get partial credit? Probably. But I don't think it's the best answer. I think the best answer is by an E2 elimination. I didn't count carbons that time because the number of carbons stayed the same. So let's count carbons. 1, 2, 3, 4, 5, 6. And bromobenzene obviously is 6 carbons. Let's see if the product is 12. 6, 7, 8, 9, 10, 11, 12. Indeed, it does. So somehow we're sticking these two pieces together. And you can see where the benzene ring goes. The benzene ring from the bromobenzene gets attached right there. Do we know any ways of making carbon-carbon bonds? We do. We learned it in chapter 9, 10. So if we can somehow convert that alkyne to this bromide, we could treat it with bromobenzene and make a cuprate out of one of them. That's the, what's his name? Oh, I'm blanking out on his name. I keep thinking Simmons Smith, but that's different. That's making the cyclopropane. Gilman reagent, that's it. So if we could somehow make this bromide, we could take bromobenzene, which we're given, and treat it first with lithium in ether or pentane, it doesn't really matter which, followed by copper 1 iodide. That makes the cuprate. And then in the third step, treat it with this bromide, and that would form a new carbon-carbon bond. That would give the product. So the only question is, how are we going to make this bromide? We need to make it from this alkyne. Let's number the carbons so we can see where they're all going. So over here, the triple bond in the starting material is between carbons 5 and 6. Now we have a double bond between carbons 5 and 6, and we've attached a bromine to the more substituted carbon. How do we turn the triple bond into a double bond and attach a bromine to the more substituted carbon? Well, by adding 1 mole equivalent of HBr to this alkyne. And that attaches a hydrogen to this carbon. This is now a CH2, and a bromine to the more substituted carbon. So with that, we have all the information that we need in order to make the compound. So we would start by taking the alkyne that we're given and treating it with 1 mole equivalent of HBr. That gives us this. So we have this. We would then take bromobenzene, which we're also given, treat it with lithium followed by copper 1 iodide. That makes the cuprate, which we talked about in chapter 10. And then we add this bromide that we made, and that will form a new carbon-carbon bond between the benzene ring and the carbon with the bromide. the reaction in general, since it's been a while, takes some alkyl halide. It's very general. The alkyl halide can be almost anything. And you can use pentane or diethyl ether as the solvent. Either is fine. That converts the alkyl halide to an alkyl lithium. And then you treat it with copper 1 iodide. That gives the cuprate. We didn't really talk much about the structure of the cuprate. It's very complicated, actually. And then with some other alkyl halide. And what you get is R1 and R2 attached. So that's the reaction. So we'll do more examples of synthesis problems tomorrow. But the idea behind a synthesis problem is, first of all, counting carbons to see where everything comes from in the product. And then starting from the product and working backwards, can you make something that looks a little more like the starting material? And how would you do that reaction? And then going from this product, can you make something that looks a little more like the starting material? And so on until you've worked your way back to the starting material. Generally, we work synthesis problems backwards from the product to the starting material. You can work forwards, I suppose. But I think it's safer to work backwards. I don't think I have time for another example of a synthesis problem. But I do want to point out that I've given practice synthesis problems on Canvas. So you can find those. They don't include any chapter 11 reactions, but it includes all the reactions in chapters 8, 9, and 10. So I'll make mention of that again tomorrow. But yeah, I think that's basically it. There was nothing else on these practice problems. Let me see if there's something else I can explain a little bit more. Let's do one example of another of these types of problems with stereochemistry. Let's say you were given this question. This is not a mechanism question. This is where you have to fill in the product. So this is going to give you the dibromide. And remember, the two bromines wind up trans to each other. So you need to show that. You're aware of that when you draw the product. we'll have one bromine on a wedge bond and one bromine on a dotted bond. Or just to clarify, you would pick either one of these two answers, not both, one or the other. You could draw it either way. They're enantiomers. That's why it says in the instructions, if the product is a racemic mixture, draw only one of the two enantiomers. That's generally the way I like these answered. So you wouldn't draw this or this. You would pick one of those structures and draw just it. But part of knowing the reaction is knowing the stereochemistry involved. And I think that's about all we have time for. So tomorrow, we'll cover deprotonation of terminal alkynes and use of those acetylide anions as a nucleophile in an SN2 reaction. And we'll also cover organic synthesis. And I have several other examples of synthesis problems, along with a step-by-step method of how to solve them in the class notes. So I guess that's about it. Last shot of the cat. He looks very comfortable. Any other questions before we leave? Why is the addition of Br2 trans? Because of the mechanism. The mechanism determines that it's trans. Remember that you get the cyclic halonium ion. You get this plus the enantiomer. I could also have drawn the methyl group with a dotted bond and the two bonds to bromine as wedge bonds. So you get this species. And then when the bromide ion attacks, it's an SN2 reaction. It has to come from behind the carbon-halogen bond. So this is to come from the top face, from the wedge bond face. It's coming from behind this carbon-bromine bond. And so that also pushes the methyl group down. So this gets you to that enantiomer. So the reason for stereochemistry is always in the mechanism. Good. Other questions? Oh, I forgot an arrow for the record. That's better. Yes, now it's correct. Good. Well, then I hope to see all of you tomorrow. And I'll try to get this onto YouTube by sometime tomorrow. Stop recording.